risk of making incorrect conclusion. Okay, because the reason of heteroscedasticity will make your the estimate of the standard error to be incorrect. Because of that, the t-statistic also is going to be incorrect, and therefore the result of the hybrid testing also will be not that reliable, not reliable. So heteroscedasticity does not destroy unbiasedness property of ordinary square method, but the method are no longer efficient. So mentioned before lah. So in terms of the estimate, the average of all possible estimates are still the same to the true value, but the estimator now no longer efficient, meaning that it's no longer has the smallest variance of the estimator. So this lack of accuracy makes the conventional ordinary square hybrid procedure to be reduced value. Therefore, if heteroscedasticity is suspected or diagnosed, then it is important to seek remedial measures. The solution, however, depends on whether the true error variance sigma I square is known or unknown. Okay. Whether the variance of this U, okay, the error term, whether it's unknown or known or unknown. Basically, normally unknown lah. Okay, but if they say we know the value, then we can use this one. But we have alternative method on for the case of unknown values. So the method of weighted least square, divided as when sigma the error variance is known. So consider the two variable regression model. Let's say we only have two variables, one dependent variable and one independent variable as given here. So assume for the moment that the true error variance is known, sigma I square is known, that is the error variance for each observation is known. Now consider the following transformation of the model. So we can, if the value is known, then we can transform the equation in order to transform the error term to have a constant value instead of instead of the unequal value. Okay. So if the value of the error bar is known, then we divide by the standard deviation, standard error. Okay. So each of the values, we divide the whole equation divided by standard error. All we have done here is to divide or deflate both the left and right hand side of the regression equation by the node sigma I, which is simply the square root of the variance. So now let this one let the error term, the transform equation with the error term to be a new error or transform error term. So we call Bi. So now this one equal to Bi, new error term. We can call the Bi the transform error term. So if Bi homoscedastic, then the transform regression does not suffer from problems of heteroscedasticity. So it is not too difficult to show that the error term Bi is homoscedastic because given that Bi equal to this one, so if the square of Bi equal to this one, Ui square over sigma I square, therefore the expected value, so meaning that the expected value of the error term, the new error term, is equal to this one. So this equal to Vi square is now equal to this one, and then so this one we can take out. Okay, sigma I square we can put out by outside. So we know that the what we call the error variance for the the expected value or the variance for the Ui square is given by sigma I square. Okay, so meaning that the variance is not as constant, but it's given by this. So ordinarily the variance of the Ui is given by this one sigma I square. So after we transform, and then we have a new error term. The transfer equation has a new error term which is Vi equal to this one. And then now after we transform, the variance of the Vi square is equal to 1. So it is constant. So meaning that we are able to, one way that what we can do is we transform the equation so that the new equation to have a constant error variance. Okay. Instead of original one, the UI, the error variance is sigma I squared. So meaning that it depends on I, it depends on x. It depends on I. So different I observation has different value of sigma. By now, after we convert, if we know the value, we transform like this. And then the transform equation now, the error variance for the new error term, Vi squared is equal to 1. Okay, so it is now a constant, meaning, which is obviously a constant. Okay. So the transform error term Vi is almost stochastic. So as a result, the transform regression model does not suffer from heteroscedasticity problem, and therefore it can be estimated by usual least square. So we can estimate using the technique that we discussed earlier, using the ordinary least square. The ordinary least square estimator of beta 1 and beta 2, beta 0 and beta 1 obtained are called weighted least squares. WLS estimator, each y and x observation is weighted or divided by its own heteroscedastic standard deviation, sigma I square. So we divide, so we know the value that we can divide. Let's divide the equation with the known sigma I. By doing so, we are able to transform the equation so that the new equation, the transform equation, the error term, the new error term in the transform equation has a constant error variance instead of heteroscedastic error variance. However, most of the time we don't know the value, but we can use the alternative way. If let's say sigma I, the error variance is not known, is unknown. Okay, so despite its intuitive simplicity, the weighted least square method requires us to know the true error variance, sigma I squared. Unfortunately, the knowledge of the true error variance is a rarity, so we don't know most of the time. In the absence of knowledge about the true sigma I squared, we could consider alternative approaches. So here we have two different cases. The first one, if the error variance is proportional to x. So as I mentioned before, so basically the first two tests, the Bush-Bargan-Goffrey, the one used to detect is the best to detect this one, in the error variance proportional to x, depends on the value of x. But then the second test we have the second test just now, it is the lecture, so proportional to x squared. So basically, if let's say the error variance is proportional to the value of x, the square of x, then we use it. We have what we call a different way of transforming the equation in order to make the error term, the new error term, to have a constant error variance. Okay. So case 1, the error variance is proportional to x, the value of x. So meaning that you have to identify percent. So first you need to identify which x. So meaning that for this given example, we only have one x. So let's say you have 2x, then you have to identify first which x is the cause of problem. For example, by retracing the square of sigma against each of x, let's see which one has the vectors of which one makes the square of residual to have non-constant or different spread, unequal spread. Okay. So you have 1 and 1. So here for this example, we have 1x. So we assume, for example, for this given example, this particular x is the source of the problem. So the error variance proportional to this x. It depends on the value of this x, xi. Okay, so error variance proportional to xi. So if after estimating the usual or the least square regression, we plot the residual against the explanatory variable x and observe a pattern that indicates that the error variance is linearly related or proportional to x, that is the variance of the error term is equal to sigma square xi. Meaning that it depends on the value of x. Okay, it's proportional to x, proportional to value of x. We state that the heteroscedastic variance is proportional or linearly related to the xi or the value of x. So what you can do, given the assumption that error variance is proportional to x, to xi, we need to transform the model in order to have the new error term to have a constant error variance. So we need to transform so that our new error term vi to have a constant error variance instead of. So this one not constant because the error variance depends on the value of x. Sigma square xi depends on the value of x. So what we can do, if we know that it is proportional to x, we have to divide. Okay, you have to divide the equation with the square root of x. The one that produces the problem. Okay. So again, you have more than one x, you have to identify which x first. So let's say you have x1, x2, and then the whole equation you divide by. Let's say x1 is the problem, so you divide by square root of x1. The whole equation. So dependent variable now, divide by square root of x, and then our intercept now becomes 1. Divide by x, square root of x. This one also, so after you divide, we only have the square of x. This one we have new error term. So our new error term vi is given by this. So whereas our vi error term equal to this, that is we divide both sides of the model by square root of xi. It can be proved easily that the error variance vi in the transform regression is homoscedastic, and therefore we can estimate the transform model using the usual least square. If you refer to this one, I provide in spectrum. So this is the proof just like before, but this for the case of unknown value. So given that vi equal to this, so the square of vi square equal to this. So you can take out this one because this one, if you square this one, then it only x now. So the square of x square, so we only have x, we take out that one. So we have this, and we know that this one, the error variance of the ui, the variance of the ui is given by this sigma square xi. So we replace this one with sigma square xi. So we can cancel this one, cancel out. So now we only have the sigma square instead of sigma square xi. Now we only have the v, the variance of the v, the new error is just sigma square, so which is a constant. Okay. So we convert, we transform. This one I provide in spectrum, so I need to copy this one in spectrum. So okay, it can be proved, now I show the program that after we transform, then we convert, we transform the error term in the transform equation to have a constant error variance instead of sigma square instead of sigma square xi. So it is important to note that to estimate the transform regression model, we must use the regression through the origin arithmetic procedure. So now, after we divide, it's just like we have two regressor now. Just like we have two regressors, this is our new dependent variable. This one, the first regressor, second regressor. So now the originally intercept now becomes just like new. In the transfer equation, just like new regressor, 1 over square root of x, square root of xi. So we must use the regression through the origin, so meaning that without intercept, this one without intercept. So because intercept, the origin intercept now becomes a new regressor. So this model, equation 1, this is equation 1, the origin 1. And then, but this model has the problem orthogonality based on the first two tests, perpagan Harvey, perpagan and laser. Harvey, I remember, Harvey also has problem. Harvey not, there's no, for the others, there's only the first two. The first two suggest there is a problem of heteroscedasticity. So how to remedy the problem? So if let's say if we believe that the error variance of this proportional to the value of x, proportional to the value of sales, then we can use this approach. So we divide the equation by the square root of the sales. Okay. So this one, maybe you estimate here, so we estimate here. estimate, or maybe you can re-estimate. You can, I mean, this one also you also can go to quick estimate equation. So you estimate the transform equation, that is the R&D expenditure, divide by square root of the sales, square root just SQR, and then the original C, now it becomes 1 over square root of sales. SQR. And then we have, you refer to this one, then this one, square root of sales, space SQR. Okay, that's okay. So we name as we can edit as one, never mind. Okay, name as question 2. So I want to have question 1 and the question that we send the next one. This one. Okay. So previously, when we perform the original equation, it fills the Butt-Pragan optic test. This one, it failed the test. Record that previously when we performed the test, Butt-Pragan optic test, it failed because p-value 0.04. But now after we transform, by assuming that the error variance proportional to the value of sales, we try this approach. We divide by the square of sales. Then if you perform the test again, you redo the test now, Butt-Pragan optic. And it's now p-value now larger than 0.5. So we managed to lessen the problem. So in terms of estimate, remember, estimate is fine. The estimate of the parameters is okay. But the problem is when there is the problem of heterogeneity, then we do have unreliable standard error, statistic, and p-value. So the reason why we transform the equation in order to help us to get more reliable estimate of standard error, statistic, and p-value, so that we are more confident to make conclusion whether the sales have significant influence or not on the dependent variable, the RD exponentials. Okay, so basically we remedy the problem in order to get reliable result or conclusion of the hypothesis testing. Yeah. But the interval estimate is okay. Estimate you can use. You can use this one because it is still unbiased estimator. Okay, we can use this estimate, the estimate of the 0.03, the estimate of the slope coefficient. So that you can say that when sales increase 1 unit, $1, for example, R&D and the expenditure on R&D increased by 3 cents, 0.03 to 3 cents. So you can use this result of estimation to make interpolation, but we are not able to rely on this because it makes the estimate of the reality incorrect. Okay, so we have to remedy and then make conclusion based on this one. Okay, so if you want a test, it says that you manage to remedy the problem, then you can form hypothesis based on this. So this one still the same conclusion. We can conclude that it is significant. Okay, now if let's say the error variance is proportional to the square of x squared, not x but x squared. If the estimated residual show a pattern, if you check the graph of residual, it shows that you can see more clearly when you produce plot between the square of residual against the x square, the square of x. So proportional to x square, which suggests that the error variance is not linearly related to x but increases proportional to the square of x. Symbolically, the error variance of u, the variance of the u or the error variance equal to sigma square xi square, not x but xi square or the square of x. So in this case, the appropriate transformation is to divide both sides of the model by xi rather than the square root of x. So divide by x, not square root of x. So each of the equation. So originally we have dependent variable y divided by x, and then the original intercept now become 1 divided by xi, and then this one is x over x, so it become 1. X over x just 1, so it's just like we have a new constant here. So it's just like we transform this to be a new intercept. Okay. And then this one is our new, the transform error term. Okay. The transform error term bi equal to ui over xi. Similarly, we can verify easily that the error term bi is homoscedastic. You refer to the this one. For the second case, if let's say error variance proportional to xi, which is given by this, the variance of ui equal to the variance of ui equal to sigma square xi square. So the transform error term in the transform equation given by this. So if you take square of this, you get this. So the variance of the vi, the variance of the new error term vi is given by this. So this one you can take out, so 1 over x squared. So we have this, and we know that the variance of u is given by this. So you can replace here. So this xi can cancel out, xi square, xi cancel out, so we have sigma square just like before. Okay, so meaning that if we believe that it's proportional to the square of x, then we divide by the value of x, not the square root of x, but the value of x, so that the new transform error term now has error variance equal to sigma square. It does not depend on x anymore, but it's just a constant value. So for a given example, let's say now we believe that, or we are based on the graph, we believe that or maybe after you perform the test, it still fail the test. You found the plug and test, you still fail the test, and then you can try this one out. Maybe it is proportional, but remember that the approach that we are going to consider, not all able to solve the problem, and sometimes the use of certain approach unable to remedy the problem. Okay, so this is just a number of available or possible approach that we can use in order to remedy the problems of heteroscedasticity, but not necessarily that the approach, each of the approach able to lessen or to overcome or to remedy the problem. So let's say if it is a proportional to x squared, so we need to divide. So we will estimate divide by sales instead of square root of sales. Sales and 1 over sales. The originally it is intercept, but now 1 over sales, and then this one sales divided by sales, it is 1, so we just equivalent to have a constant, you put still. So the question now, basically this is represent the estimate for the slope for sales original equation. So our C here is the estimate of the slope parameter for the sales in the original equation. But what we want to do now, we want to have reliable estimate of standard error. So reliable or not, so we have to test that. So in this case, so if you perform the test again, heteroscedasticity test, perparakan complete test, it's a p-value, even better than previous one, I think. So this one 0.22 greater than 0.05. So meaning that we can rely on this now to perform hypothesis testing. So we see that we reject the analysis, we conclude that sales have significant influence on the R&D expenditure. Okay. In terms of estimate, you can just use this one. Okay, the original estimate is fine. You can use it because it's still unbiased. It is unbiased. The problem is here. The problem is on the standard error. Okay. But this one also quite similar lah. So notice that an interesting feature is that what was originally the slope coefficient now become the intercept. Okay, this one. What the originally the slope coefficient was for the sales beta 1 now become an intercept. And that what was originally the intercept now become the slope coefficient. Original intercept now become slope. This change, however, is only for estimation in order to provide us the reliable estimate of the standard error. Multiplying by the xi on both sides, we get back the original. Okay. So this one I do want that first now. So there are two possible ways of to elevate the problem. So the next possible approach that to re-specify the model. So re-specification of the model. Instead of speculating about the value of the sigma I square, the error variance, sometimes a re-specification choosing a different function form can reduce heteroscedasticity. For example, instead of running the linear invariable regression, if we estimate the model in log form, it often reduces the heteroscedasticity problem. That is, if we estimate log of dependent variable against log of the independent variables, the heteroscedasticity problem may be less serious, or maybe we are able to overcome the problem, totally overcome the problem. So the log transformation compresses the scales in which the variables are measured, thereby reducing a tenfold difference between two values to twofold difference. As an example, let's say in the original values of y or x, the value is 90, which is 10 times of 9. So after we use log transformation, we compress the value. So log of 90 now is equal to 4.49, which is only twice as large as the log of 9, which is equal to 2.1. So we compress the value to make smaller. So by doing so, it can help to reduce to have the model to reduce to have what we call that the different value of the error term, different value of the error variance. Okay, so it helps to make the error variance to be not that much different. Okay, based on across different value of x. So for this given example, another possible solution is by using different functional form instead of using original R&D and sales variables. We use log, double log model for example. So log of sales, log of R&D expenditure, and then log of sales. So you have Okay, so you have more than one x, you can apply log transformation on all x. No? So let's say if I have another x2, you can log of x2 as well. Okay, so we get this one. So now the question is, this one reliable or not? For us to conclude whether the log of sales significantly influence the log of the, or you can interpret as before. I mean, because the log model you can interpret as electricity percent. Okay, I mean interpretation okay lah. You can interpret as this one. It's okay. The estimate is still unbiased. But this one whether the hypothesis it is reliable or not. So you perform the test as before. Let's say you just perform the test using the one of the tests, one problem corporate. It is now the pass the test 0.1. If you perform the test at 5% level, now it is p value greater than 0.05, so we do not reject. Conclude that there is no heteroscedastic. I mean the variance are not, the error variance are not different. It's just the same, be constant. Based on the tested what we call that the test that we use for the corporate, the tested pattern of the error, the heteroscedastic error. Okay, but you can also perform the test as well. So this one we just, let's say we just perform the test using the problem test. Now using the use of different point form allow us to improve the to make the model now pass the Volkswagen corporate. Other possible solution: redefine the variables. Regress per capita dependent variable against per capita independent variables. For example, in the study of expenditure on travel and the corresponding income for 51 cities or countries, we might expect that the error variance are heteroscedastic and increase with population size. Cities, countries with large population are likely to have greater variation in the expenditure on travel than small. So let's say you collect data. Let's say you have two variables. You want to explain the travel expenditure. Your Y is travel expenditure so your dependent variable is one, expenditure on travel. Okay, and then you collect data total amount of expenditure from different cities. Okay, for example, you collect data the total amount of expenditure on travel for Kuala Lumpur, for example, and then you also has the total amount of expenditure for other smaller cities. Then you have the problem like before. So for example, this one, whenever you have this one, so for example, let's say you have the travel expenditure and then you have total income. Okay, total income for everyone, I mean for the whole population. So let's say for KL, for Lumpur, you have this one. Then this one for smaller cities, Ipoh for example, or other Alustar. So because of that, you will have the problem because you have some of the observation has small value of Y and X, and then other value of X, Y and X has large value of Y and X, and then you can produce the different value of error term. So this one has smaller error, this one has large value of error, and then you make your error variance to be different. So in order to overcome the problem, one possible way is to calculate or to use the per capita variable. So meaning that you divide by number of people So let's say income total expenditure in KL, Kuala Lumpur, you divide by number of population, how many people in Kuala Lumpur, so that you get average of expenditure per person. Okay. And you do the same for the other cities as well. For Ipoh, in Ipoh, you divide, you calculate the average expenditure and average income for each people in Ipoh, for example. So you, by doing so, you are able to lessen the problems of heteroscedasticity, or even to avoid the problem. Can use the per capita variable. So for the example that we had before, it's also possible if you are able to get, for example, this one you have the problem. This one we have R&D expenditure and sales. So if there is any way for you to recalculate, so you get average instead of the total sales, total R&D expenditures, you are able to recalculate and use the average value, and you may be able to remedy the problem. I mean, to avoid the problem of accuracy as well for this data. Okay, if you are able to do so, you can do that. You can consider to do it. Use the per capita or the average, for example. Okay, instead of the total amount, because different size of companies here has different values of sales, larger company has larger sales and R&D expenditures compared to smaller companies. So this one, you have this kind of data, so calculate, use regress per capita against the per capita for the other independent variable. The last possible way is using the robust standard error. So this one we call the white heteroscedasticity corrected standard errors. As we have noted in the present of heteroscedasticity, there are all really square estimator. Although unbiased are inefficient, although the average or all possible estimate are equal to the true value, but it is no longer efficient. So meaning that it affects the variance of the estimator. So as a result, the conventionally computed standard errors and the t-sensitivity of the estimator are suspect. White has developed an estimating procedure that produces standard error of estimated regression coefficient that takes into account heteroscedasticity. As a result, we can continue to use the T and F test for hypothesis testing, except that they are now valid asymptotically, that is in last sample. It is advisable to present the usual standard errors as well as the white heteroscedasticity corrected standard error for comparative purpose, but keep in mind that white methodology is strictly speaking applicable in last sample. So if you want to use this approach as a remedial measures, you have to make sure you have enough data set, large sample size. Okay, so when we talk about large sample size, normally large sample size refers to the observation greater than 30, but this one you should aim to have larger. Now you want to use this one, try to have larger sample size. That's why last week I mentioned to you, try for your group assignment, try to have at least 50 observations. Okay, if you refer to one of the reference book, textbook, reference book, it has one example of the solution for heteroscedasticity using this one, robust standard error, and for that example, it has about 45 observations. So I mean, 45 still okay lah, but try to have, I encourage you to have at least 50 or 50. Even larger is better. Okay, larger is better to produce more reliable estimate. So how to use this approach? When you estimate the model, for example, this one we estimate the model, the original model, RD, C, sales. You go to option. You select, instead of ordinary, you select, I think this one Huber White. Huber White, it will produce an estimate. It produces an estimate of standard error that is less or unaffected by the present of heteroscedasticity problem. Okay, like this, then okay. But this one, we have to trust them. Meaning that's why I mentioned earlier. You need to make sure you have large enough sample size, because we are able to check whether the use of this approach managed to lessen the problem or avoid the problem. Because if you perform the test again, it produces the same test, the same result of test. For example, if you perform a test, heterogeneity, basically it produces the same test like the original model. So basically this one you have to trust. You do the approach, you have to make sure you have sufficient data, and then we just trust that now the estimate of the error is reliable for us to make hypothesis statement. But this one, for this example, it's not. You should not trust that, because it is. We have small sample size, 18 only. Okay. So 18, you should not perform. You should not use the approach for this example, because we have small sample size. This one I just show you how. So if you want to use this approach, robust error, then you have to make sure you have large enough sample size. Okay. Try to have 50 or around 50 or above. But there is an example given one of the books. He used 45 observation for this approach. So 45 is still acceptable. So you notice that the original, this is the original estimate. The estimate exactly the same after you use the robust error. The estimate is exactly the same. So I mentioned before that the estimate in the model is okay. It does not. I mean, even though it may not close to the true value, but it is still unbiased. But the problem when we have a heterogeneity problem here, we have a problem with the error. So by using robust error, it helps us to provide more reliable. But this one we cannot. I mean, we cannot use actually in the real practice. You should not use for small sample. So we have 18 observation. Okay. So we still have about 20 minutes. Maybe we can do the first question for the lab session 6. Okay, the expression about robust error given here. You open this. Basically, we have different types of robust error, estimated offset error. The one that we used just now, then you go wide. You read here, basically we have this one. For the case of heterogeneity, we can use this one, the NC. But later, next week, we discuss about autocorrelation, and we can use this one. Autocorrelation, heterogeneity, and autocorrelation for system covariability. So we have almost, okay, so question number 1, what is meant by heterogeneity? That as what we discussed earlier, so I explained to you that it represents the problem when we have we have a different what we call error variance, not constant error variance. Heterogeneity means that the variance of the error term in a regression model does not remain constant between different observations. The reduced square estimated are still unbiased, but they are no longer efficient. So estimate we can use, but in terms of hypothesis testing, then we have problem for hypothesis testing. Since the estimated standard error of the reduced square estimated may be biased, the resulting t ratios are likely to be biased too. As a result, usual combined interval, testing procedure, etc. are likely to be of questionable value. So question number 2, we have almost the same data, but now we have different variable profit. Try to redo it, but try to just use now. Later at home you can do the manual one, the manual approach. So this one, question number 2. Estimate regression by regressing the RID as mentioned against profit. So you can estimate the usual RD, EXP, space C and profit. Obtain residual and plot against the equity variable related any evidence of capacity. So you can produce plot. So this one okay. So you go to view actual fitted residual table. So you have this actual fitted y hat residual. You can see residual for different value of x. Now you have larger spread of residual, value of residual. The size of residual getting bigger. Okay. So now if you want, the question asks you to plot the residual against the value of x, the profit. So residual against profit, you can just let's say now we want to produce plot, scatter plot, profit as your x axis, residual as y axis. So you have to click profit first, and then click the receipt. Price control, click the receipt. You can right click, open as group. You go to view graph, scatter plot. So based on graph you can see now. So as the value of profit increase, the size of the error, estimate of error, residual, the value, the spread getting larger, the spread. So there seems to be some evidence of heteroscedasticity in the data, in the model. C, verify your qualitative conclusion by conducting the brush-bug offering, Kaiser, Harvey, and Hodge test. So, the estimated model just now, you can perform the test. So this one again, I'm not sure the manual one. You can do the manual one again at home. So you just use in-use. So again, I mentioned for your midterm test, just use in-use to produce the result. Not need to do manual approach. So you estimate the model. For example, this one you estimate, you get the result. And for the test, just go to view, residual diagnostic, heteroscedasticity test. Perform the test using the 3 tests. Brush-Pagan, 4 tests. Brush-Pagan, laser, Harvey, Hodge. So for the Brush-Pagan, the result suggests there is heteroscedasticity problem. How about laser? This one also the same. Okay, and Harvey Hodge. Harvey also failed. How about Hodge? Hodge also failed. So you failed all 4. So after you remedy, basically the good idea is that you test for all. I mean, for example, we remedy problem and we just perform the test using Brush-Pagan. But it's good that you perform using all the tests. Although it's not compulsory, as mentioned before, you refer to the article. For example, some of them just use white test. But again, you refer to the example given in lecture, the white test failed to detect a problem. It says there is no problem, but the bus button says there's a problem. That's similar with the laser test as well. Okay, so it just so you have to decide whether you are willing to take the risk, meaning that white test has a less chance of capturing the problem, but it is acceptable to use it. So this one, the next question, if there is evidence of heterogeneity, how do you transform the data? So in terms of transform, we have a weighted square, so we have 2, whether we assume it is the error value proportional to x or proportional to x squared. So we can try the first assumption. So let's say the first assumption that it is proportional to x, then we divide by square root of profit. Okay, this one. So you estimate. Maybe we estimate another one. So we estimate the transform equation. So we have RDEXP space divided by square root of SQR of profit. And then the original intercept now become 1 over square root profit. And then we have profit divided by square root profit, we have square root profit. So okay, so name as equation 2 or equation 1. So this is the transform. So now the question is, the original one is 1, the original, this is the original, estimate 0.36, this is the transform equation 0.37, it's slightly different. Now the question is whether this is reliable or not. The original one not reliable, this is not reliable because we have a problem. So this one reliable or not, so you perform the test. For example, you perform the test, perception test. So it still failed, 0.03 less than 0.05. So the use of the first assumption, proportional to x, is unable to remedy the problem, still failed the test. So now consider another assumption. If let's say we assume that the error value proportional to x squared. So if proportional to x squared, what you do? You divide by profit, not square of profit. So divide by RAD expenditure, divide by profit itself. And then our original intercept will become 1 over profit. Profit divided by profit equal to 1, it becomes a new constant. Okay. So now this is reliable to perform the test again. You perform the test. You see heterogeneity berpakan. Now it is created that. So meaning that the error variance for this is proportional to x squared. Then not instead of x is proportional to x squared. So you use this one to resolve this. alternative approach is by using different re-specify the model or using different functional form. Question number 3, yeah. Question number 3, use different functional form using log. So instead of using original values, we try to use log. So we re-estimate using log. So log of R&D expenditure, R&D exp, spacey log profit. But in interpretation, you have to be careful. So you have to interpret at percent this one. Because using double log model, interpret at percent. Elasticity, you cannot interpret as usual. You have to interpret as elasticity. So when profit increase 1%, the R&D expenditure increase how many percent? By 99%. No, 0.99%, not 99%, 0.99%. Okay. So this one reliable now. Can we make harmonious testing based on this? Can we set the result of harmonious testing based on this? So you test now. For the test, let's say just one copy. Now it is okay lah. So we can use. Yeah. For 3B, apply code fact one. That one I leave it to you to do at home. You need to sort using the sorted data. So we have using the sorted. So we need after sort from smaller to higher, and then you remove the middle one. Just like what we did earlier, and then estimate the first part, second part, the first subsample, second subsample, and then you calculate. Question number 4. A48 next week. So question number 4 we done this week. Can or you want to start now? Next week. So I just afraid that some of you want to get past. We have to leave before 9.